We're now in Physical Chemistry, Chapter 12, Section 4. The fourth colligative property is osmotic pressure. Let's say that we have this container here. We've got some sort of membrane between two parts. Now this membrane is permeable to only substance A. Now on this left side, we have pure A, but over here, we have a solution to substance A and substance B. Now, these are not entirely closed. They're open here, so you've got a certain pressure down here on the left side. We've got a certain pressure down here on the right side. And then, of course, for the pure A, the chemical potential will be mu subscript A star, because it's the pure substance. And then over here, the chemical potential of just the substance A would be just the chemical potential of substance A. Now we're also going to say that this is thermally conductive, but that's not necessarily important right now, just that these two are the same temperature. Now we're going to start out so that the two liquids, they start out at the same height, so they're level. So like I said, P subscript L is the pressure down here on the left side, P subscript R is the pressure down here on the right side. So we're going to start out, initially, our starting conditions, with the pressure on the left side is equal to the pressure on the right side. Now, initially, the chemical potential of the pure substance A is actually going to be greater than the chemical potential of the substance A in the solution. Now, what that means is, remember, A is our solvent. So, A is going to migrate from left to right. Now remember, B can't migrate because the membrane is permeable only to A, not to B. So if we have the solvent, substance A, flowing from the left side to the right side, obviously you expect the liquid level on the right side to rise, and vice versa, the liquid level on the left side to go down. So after that, the chemical potential of A is going to be equal to the chemical potential of the pure substance A plus the gas constant R times the absolute temperature times the natural log of the mole fraction of the substance A. And there's going to be continuous migration from the higher potential to lower potential. So we have chemical potential of substance A, pure state, that's equal to the chemical potential of A on the left side, which is greater than the chemical potential of A on the right side. Now remember, we know that the partial derivative of the chemical potential of substance A with respect to pressure, holding temperature constant, is equal to the average molar volume of substance A. Now we also have the differential of the Gibbs free energy is equal to minus the entropy times the differential of temperature plus the volume times the differential of pressure. Now we're going to assume constant temperature for now, which means the differential of temperature is going to be equal to 0. Now we know the average molar volume of A, a substance A, is going to be greater than 0. And we also know that the partial derivative of the chemical potential of substance A is going to be greater than 0. So, therefore, the partial derivative of the pressure has to be greater than 0. Now we're going to use the capital Pi to denote osmotic pressure. Now let's say that P is equal to the equilibrium pressure on the left side. Then we have P plus the pi for osmotic pressure. That's going to be the equilibrium pressure on the right side. So remember, this pi is this extra pressure that we must apply to the right side in order to make the chemical potential of substance A on the left equal to the chemical potential of substance A on the right. Obviously, at equilibrium, we know that the chemical potential of A on the left has to be equal to the chemical potential of A on the right. Now, the chemical potential of A on the left, remember, of course, is the chemical potential of pure A at whatever temperature and pressure. Now, The chemical potential of the right is going to be the chemical potential of the pure substance A, but at the pressure, original pressure, plus the osmotic pressure and temperature. And then also plus the RT ln, and then gamma A chi A. So remember chi A, that's our mole fraction. And then, yeah. So we have the differential of the chemical potential of A in the pure state. That's equal to the differential of the Gibbs free energy, the molar Gibbs free energy of substance A of the pure stuff. So we have minus the molar entropy of substance A in the pure state times the differential of temperature plus the molar volume of substance A in the pure state times the differential of pressure. So this is the Gibbs equation applied to the pure solvent. Now remember, we've been saying that temperature is going to be constant. So this whole term, the mole minus the molar entropy of substance A in the pure state times the differential of temperature is going to be equal to 0. Because at constant temperature, obviously the differential of temperature is equal to 0. So then we have the differential of the chemical potential of A in the pure state is just equal to the molar volume of substance A in the pure state times the differential of pressure. So we're going to take the integral of that from the original pressure to pressure plus the osmotic pressure, and with the differential of chemical potential A star. So it's the integral from the original pressure to the final pressure, which is the original pressure plus the osmotic pressure, of the molar volume of substance A in the pure state times the differential of pressure. Now we're going to use P prime for now as a dummy integration variable, just to see what happens. So that we get the chemical potential of A in the pure state at whatever pressure plus the osmotic pressure at temperature minus the chemical potential of A in the pure state at the original pressure and temperature, and that's equal to the integral of from the original pressure to the pressure plus the osmotic pressure of the molar volume of substance A in the pure state of dP prime. Now remember, liquids aren't really compressible, so we're going to say that the molar volume of substance A for the pure state is roughly constant, just like you would do for pretty much any solid or liquid. So the chemical potential of substance A in the pure state of the pressure plus the osmotic pressure and temperature minus the chemical potential of A in the pure state of the original pressure and temperature is equal to, see, we pulled out the molar volume of the pure substance A in the pure state times the integral from the original pressure to pressure plus the osmotic pressure of dP prime. So that's easy because if we just get that out. So we get that's equal to the molar volume of substance A in the pure state of P plus pi minus P, so those cancel out. So we end up with just the molar volume of substance A at the osmotic pressure. So the chemical potential of the substance A in the pure state of the original pressure plus the osmotic pressure at original temperature minus the chemical potential of A in the pure state of the pressure and the temperature is equal to minus the gas constant R times the temperature times the natural log of gamma of A and chi of A. So that gives us minus RT ln gamma A chi A is equal to the molar volume of substance A in the pure state times pi, our osmotic pressure. Now we can just solve for pi, and we get the osmotic pressure is equal to minus RT divided by the molar volume of A in the pure state times the natural log of gamma A chi A. And this is true for any solution, because really the only assumption we made was, that it's the molar volume is constant because it's not compressible. Now for an ideally dilute solution, we said that the natural log of gamma A chi A is roughly equal to minus the mole fraction of B. So substituting that in, pay attention to the minus sign, now we get pi is equal to R the gas constant, times the absolute temperature, divided by the molar volume of A, still in the pure state, times the mole fraction of the other substance, our solute, which we're calling B for now. And remember, we said for an ideally dilute solution that gamma A is equal to 1 anyway. So natural log of the mole fraction of A, remember, is equal to natural log of 1 minus the mole fraction of B, since we only have two substances, which is equal to minus the mole fraction of B. That's how we did that substitution. So we have the osmotic pressure is equal to the gas constant R times the absolute temperature divided by the molar volume of A star of the solvent times the mole fraction of the solute. And like I said, B is the solute and A is the solvent. So we have the mole fraction of B is equal to the number of moles of B over the number of moles of A plus the number of moles of B, since there are only two substances. Now, since the number of moles of A is much greater than the number of moles of B, since we're talking about an ideally dilute solution, then the mole fraction of B is basically just the number of moles of B divided by the number of moles of A. So we get the osmotic pressure is equal to the gas constant R times the absolute temperature divided by the molar volume of the pure substance A times the number of moles of B divided by the number of moles of A. Now remember, the volume, again, because it's ideally dilute, we're going to kind of neglect B. So we get the volume is the number of moles of substance A times the molar volume of A in the pure state. And we're just going to say the P prime is P, because we're just using P prime as a dummy. So the volume is going to be roughly equal to the number of moles of A times the molar volume of substance A in the pure state. Again, that's just because we're assuming an ideally dilute solution. So the number of moles, the volume, the molar volume of substance A in the pure state, remember, is just the volume divided by the number of moles of A. So what we get is that the osmotic pressure, pi, is equal to RT over the volume divided by the number of moles of A, and then times NB over NA. So these NAs are going to cancel out. So we get the number of moles of B times R times T divided by V. Now remember, the number of moles of B divided by the volume, that's also known as the concentration of B. So we could also just say that the pi, the osmotic pressure, is equal to the concentration of the solute times RT. So remember, C subscript B is molar concentration of your solute. And of course, pi is osmotic pressure. So the P pressure is the number of moles divided by the volume times RT. And remember, that's where N divided by V is just the molar concentration. This is just like this is the ideal gas law. But in this, for this liquid form, concentration, pi is equal to the concentration of B RT. This is called the Hoff Law. And this is only true for very dilute solutions because of those approximations we made about volume and so on. Now for these types of calculations, it's useful to use R in the form of 0.08206 liter atmospheres per mole Kelvin. Now pi is going to be I CBRT. So we're going to say I is equal to 1 for non-electrolyte. Now if we are talking about an electrolyte, I is going to be greater than 1. We're calling this lowercase I the Van Hoff factor. Now for example, let's say we have calcium chloride, I is equal to 3. Because when you split it into ions, for each molecule, you're going to get 1 calcium ion and then 2 chloride ions. So that's 3. Okay, so here's a graph of pi versus concentration. So remember, pi is our osmotic pressure, and we're doing it in atmospheres. And then our concentration, that'd be like in moles per liter, but it doesn't really matter, it just changed the size of the graph. So you'll notice here, based on that Van Hoff law, you would expect this to be a straight line. So the slope of this line is RT, and this line is assuming that we have an ideally dilute solution. And of course, that's assuming we have constant temperature. Now, for comparison, a real solution is going to go up higher than that, like this. Now, let's say, here's an example again. We're going to say we have pure water and we have a solution, like salt water or whatever. We can actually do the reverse of what we just talked about. Reverse osmosis is when you apply pressure to the right side here, the side with the solution, so that you get more of the pure solvent out on the left side. In this case, obviously, water is the solvent. So this is one way they can purify water. So if you increase pressure on the right side, then you're going to get the chemical potential of the substance A on this side greater than the chemical potential of the pure A over here on the left, which means forcing it to go backwards. Now, in real life, you can do this with seawater. The osmotic pressure is, 600 to 900 psi. So if you apply that much pressure, you drive it backwards. Now, of course, calling this a membrane is simplification. It's actually might be a whole stack of over 1,000 membranes. There's actually a company in Bend that does this stuff. Now, here's another example for those of you who are interested in biology. Let's say that we have a cell. And then your cell is surrounded by fluids. Like it could be tree sap in the case of a tree, it could be lymph or blood, whatever the type of cells are. So your cell can experience this osmotic pressure too. Now there are three possibilities here. Now let's say that the concentration of the fluid out here in the surroundings is greater than the concentration in the cell. Well, in that case, we say that it's hypertonic and the cell shrivels. So we say that the surrounding is hypertonic, which basically means that the osmotic pressure of the surroundings is greater than the osmotic pressure of the cell. So what will happen is that your fluids will leak out of the cell. Now the second possibility, if you have the concentration of the fluids in the surroundings going to be less than the concentration of the fluids in the cell. Well, then we say it's hypotonic, and the cell is going to expand, because what's going to happen is it's going to, soak up liquid. The fluids go into the cell, and it just keeps growing and growing and growing until the cell actually can burst. Now, this is we say the surrounding is hypotonic. Then, the surrounding is hypotonic. So that means the osmotic pressure of the surroundings is less than the osmotic pressure in the cell. And of course, then the third case is if the concentration of the fluid in the surroundings is equal to the concentration fluid of the cell, then we say the surrounding is isotonic with the cell, which means they have the same osmotic pressure. The osmotic pressure in the surroundings is equal to the osmotic pressure in the cell. Okay, that is the end of section 4.